Headlines frequently discuss nuclear programs, uranium enrichment, and regional security concerns. But what do these terms truly signify? Beyond the political discourse, there's a fundamental scientific process at play. Understanding this science is crucial for comprehending one of the most significant geopolitical issues of our time, the dynamics between Iran and Israel. Today, we're going to explore uranium enrichment. We'll examine the fundamental physics that makes it possible, its various applications, and how this scientific process has become a central point of international focus. This discussion extends beyond abstract science. It touches upon global security, regional stability, and the complexities of nuclear proliferation. By the end of this video, you'll have a clear, scientific understanding of what uranium enrichment entails and why it draws such significant international attention. We'll begin with the basics of atoms and isotopes, then delve deeply into the methods of enrichment, primarily centrifuges, and how they achieve such precise separation. We will also touch upon other key fissile materials. Finally, we'll concisely connect these scientific concepts to the specific context of Iran's nuclear program and the security considerations of regional actors. Let's begin. To understand enrichment, we first need to get microscopic. Everything around us is made of atoms. At their core is a tiny, dense nucleus, surrounded by a cloud of orbiting electrons. The nucleus itself is composed of two types of subatomic particles, positively charged protons and neutral neutrons. The number of protons in an atom's nucleus is what fundamentally defines an element. For instance, an atom with 1 proton is always hydrogen, 6 protons define carbon, and 92 protons define uranium. Each element has unique chemical properties determined by its electron configuration, which in turn is dictated by its proton count. Here's where a key concept, isotopes, emerges. While the number of protons defines an element, the number of neutrons in an atom's nucleus can vary. Atoms of the same element that have different numbers of neutrons are called isotopes. They are chemically identical but differ slightly in mass. For uranium, there are two primary naturally occurring isotopes relevant to nuclear technology: uranium-238 and uranium-235. Natural uranium mined from the Earth is overwhelmingly uranium-238, constituting about 99.27% of the total. Uranium-235, the rarer but critical isotope, makes up only about 0.72%. The mass difference, though seemingly small, is significant. Uranium-238 has 146 neutrons, while uranium-235 has 143. This subtle difference in mass is the physical property that all enrichment processes exploit, as chemical separation is ineffective. While uranium-235 is the only naturally occurring fissile material in significant quantities, it's important to note that it's not the only material capable of sustaining a nuclear chain reaction. Plutonium-239 is another crucial fissile material. It is not found in nature in significant amounts but is produced in nuclear reactors when uranium-238 absorbs neutrons and undergoes a series of radioactive decays. A third fissile material, uranium-233, can be produced from thorium-232, which is more abundant than uranium. This process also involves neutron absorption within a reactor, converting the fertile thorium into fissile uranium-233 through intermediate decay steps. These three, uranium-235, plutonium-239, and uranium-233, are the primary fissile materials used in nuclear technology. Our focus today, however, remains on the process of enriching natural uranium to increase its uranium-235 content. Now, let's understand why uranium-235 is so critical. It's fissile, meaning its nucleus can readily split when struck by a slow-moving neutron. This splitting is called nuclear fission. When fission occurs, the uranium-235 nucleus breaks into two or more smaller nuclei, known as fission products. This process releases a tremendous amount of energy, far greater than any chemical reaction. Crucially, fission also releases additional neutrons, typically 2 or 3. These newly liberated neutrons can then go on to strike other uranium-235 atoms, causing them to fission, releasing more energy and more neutrons. This cascade is known as a nuclear chain reaction. In a nuclear power reactor, this chain reaction is carefully controlled to produce a steady release of heat, which is used to generate electricity. In contrast, for a nuclear weapon, an uncontrolled, rapid chain reaction is initiated to release all that energy in an instant, resulting in an explosive force. The concentration of uranium-235 directly determines whether a controlled reaction is possible, or if an uncontrolled, explosive reaction can occur. The challenge of enrichment lies in the fact that uranium-235 and uranium-238 are chemically identical. They behave the same way in chemical reactions. The only physical property that distinguishes them is their tiny difference in mass. Uranium-238 is just slightly heavier. Separating these nearly identical isotopes is an incredibly demanding technological feat, likened to sorting grains of sand based on a microscopic weight difference. Historically, one of the first industrial-scale methods employed for enrichment was gaseous diffusion. To utilize this, uranium is first converted into a gaseous compound called uranium hexafluoride, UF6. This gas is then pumped through thousands of porous barriers or membranes. Due to their lighter mass, the uranium-235 molecules of UF6 move slightly faster and, therefore, pass through the tiny pores more frequently than the heavier uranium-238 molecules. This separation effect in a single stage is minuscule, requiring hundreds, even thousands, of stages connected in series to achieve significant enrichment. Gaseous diffusion plants are enormous, consuming vast amounts of energy to power the pumps and maintain the gas flow, making it a highly energy-intensive and costly method. Today, the most prevalent and significantly more efficient method is gas centrifuges. Imagine a tall, cylindrical rotor spinning at incredibly high speeds, often exceeding the speed of sound at its outer wall. Uranium hexafluoride gas is fed into the centrifuge. As the cylinder spins, the heavier uranium-238 molecules are flung outwards towards the centrifuge wall by the immense centrifugal force, while the slightly lighter uranium-235 molecules remain concentrated closer to the central axis. This creates a subtle separation gradient within the spinning gas. Internal scoops or pipes then draw off the slightly enriched gas, higher uranium-235 concentration, from the center and the depleted gas, higher uranium-238 concentration, from the periphery. This tiny enrichment gain from a single centrifuge is then amplified. Thousands of these centrifuges are connected in a series, forming what are known as cascades. The slightly enriched output from one centrifuge becomes the input for the next, progressively increasing the concentration of uranium-235 to the desired level. This cascade arrangement allows for the fine-tuning of enrichment levels and makes the process far more energy efficient and compact than gaseous diffusion. The level of enrichment is a critical factor, directly determining the uranium's application. Low-enriched uranium, LEU, typically enriched to 3 to 5% uranium-235. This concentration is sufficient and safe for use as fuel in most commercial nuclear power reactors, providing a controlled and sustained chain reaction for electricity generation. It cannot be used to make a nuclear weapon directly. Highly enriched uranium, HEU, enriched to 20% or more uranium-235. This level is significantly more potent. For nuclear weapons, uranium is typically enriched to approximately 90% uranium-235, referred to as weapons-grade uranium. This high concentration allows for a rapid, uncontrolled chain reaction. It's important to understand that while reaching 3 to 5% enrichment requires substantial effort, increasing enrichment from 20% to 90% requires comparatively less additional effort and time than the initial jump from natural uranium to 20%. The ability to enrich to lower levels fundamentally demonstrates the technical capacity to achieve much higher levels, given sufficient time and centrifuges. Iran's nuclear program began in the 1950s, with stated objectives of peaceful energy generation. However, its development, including facilities like Natanz and Fordow, has consistently been a subject of international scrutiny, raising concerns over its transparency and potential applications beyond peaceful uses. In 2015, Iran and world powers reached the Joint Comprehensive Plan of Action, JCPOA. This agreement strictly limited Iran's enrichment activities, capping it at 3.67% uranium-235 and reducing its centrifuges, in exchange for sanctions relief. The aim was to extend Iran's breakout time, the estimated time to produce enough weapons-grade uranium, to over a year. Following the U.S. withdrawal from the JCPOA in 2018 and subsequent reimposed sanctions, Iran began to incrementally exceed the agreement's limits. It increased enrichment levels, reaching 20% and later 60% uranium-235, and expanded its centrifuge research and deployment. While 60% is not weapons grade, it significantly shortens the path to 90% and has heightened security concerns for regional actors. The advancements in Iran's enrichment capability have intensified security concerns for various regional actors, notably Israel. Their leaders have consistently stated their commitment to preventing the acquisition of nuclear weapons by Iran, viewing its nuclear progress as a significant regional challenge. This underscores the strategic importance of breakout time, the estimated period Iran would need to enrich uranium for a single weapon if it chose to do so. With higher enrichment levels and increased centrifuge capacity, this critical window has notably shortened. While diplomatic efforts to address these concerns continue, the evolving technical capabilities and regional dynamics highlight the ongoing complexities. Understanding the scientific intricacies of uranium enrichment is key to grasping the core issues at play in this significant geopolitical challenge. I hope this video helped clarify the science behind uranium enrichment and its role in the geopolitical landscape involving Iran and Israel. If you found this explanation useful, please give this video a like, share it with others who might benefit from this insight, and subscribe to our channel for more science-based explainers on complex global issues. Let me know in the comments below what other complex topics you'd like us to unpack next. Thanks for watching.